our evening. So, okay, so we can start. We will start in Polish, me and Paweł. Then we will give a floor to Aleksander and Krzysztof, and the evening will be yours. Szanowni Państwo, serdecznie witamy na kolejnym wieczorze WEinnovators.Club. Słyszeliśmy, że już się Państwo trochę za nami stęsknili, bo była krótka przerwa. Bardzo za nią przepraszamy. Jedna nie wynikała, znaczy nie była naszą winą, tylko spowodowana była COVID-em tak naprawdę, trzeba to powiedzieć. Cieszymy się, bo dzisiejszego wieczora mamy nadzieję, że dowiemy się, znaczy ja i Paweł, dowiemy się, czym jest inżynieria procesowa. Systemowa, przepraszam bardzo, ponieważ mieliśmy taką dyskusję, rozmawialiśmy sobie u nas w biurze. Jedna inżynierka powiedziała, no moim zdaniem to jest wszystko, czym się zajmuje inżynieria, ale tak naprawdę dzisiaj dowiemy się wszystkiego. Są z nami fantastyczni goście. Dziękujemy za zaproszenie do naszego grona, do naszego wieczoru Davida Longa, który jest absolutnym guru, jeżeli chodzi o inżynierię systemową. Mamy też dwóch polskich prowadzących, którzy poprawcie mnie, jak się nazywa po polsku wasze stowarzyszenie?
To jest INCOSE, czyli Stowarzyszenie, można powiedzieć, Inżynierów Systemowych po prostu.
Dobra, dałbym radę. Tutaj. Dziękujemy bardzo za zaproszenie naszego gościa. Paweł, co nas czeka w najbliższych tygodniach?
To zanim jeszcze powiem, co nas czeka w najbliższych tygodniach, to powiem, że to jest pierwsze takie spotkanie, w którym tak naprawdę oddaliśmy naszym uczestnikom ten środowy wieczór, bo cała inicjatywa tego spotkania, jego temat, pomysł na to spotkanie wyszła właśnie od Krzysztofa i Aleksandra. Bardzo Wam za to dziękujemy, bo ten klub, można powiedzieć, że my jesteśmy jego administratorami, natomiast to nasi uczestnicy są najważniejsi i robimy to dla Was, więc im więcej Waszej inicjatywy, tym bardziej nas to cieszy. A jeżeli chodzi o inżynierię systemową,
to powiem, Paweł próbował tym zdaniem subtelnie powiedzieć, że jeżeli macie pomysły na to, kogo można zaprosić, macie jakieś kontakty i chcielibyście dołączyć do roli prowadzących, bo oczywiście my chętnie tę rolę oddajemy i przekazujemy, ponieważ lubimy ludzi, otaczać się ludźmi inteligentnymi, to serdecznie zapraszamy.
To ja jeszcze powiem tylko o jednej próbie wyjaśnienia, czym jest inżynieria systemowa. Też podczas pogłębionych rozmów z naszymi inżynierami, kiedy już zupełnie nic nie rozumiałem z tego wszystkiego, to kolega powiedział, że to jest tak, że są lekarze bardzo wielu specjalności, ale najlepszy lekarz to ten, który jakby całościowo rozumie ludzki organizm, który jakby rozumie jego procesy, nie w oderwaniu nie patrząc na to, jak działa nerka, głowa czy ręka, a rozumie jakby złożoność organizmu jako całość i że ten potrafi najtrafniejszą diagnozę postawić. Więc być może jest to, resztę dowiemy się w trakcie spotkania. Tylko tytułem jeszcze wstępu, co nas czeka właśnie w tych następnych spotkaniach. Przed świętami jeszcze spotkamy się z Juanem de Dalmau, to jest prezydent International Space University i to spotkanie będzie poświęcone kosmosowi, jak rozpocząć skutecznie jakby karierę w branży kosmicznej, a już po świętach spotkamy się z byłym prezydentem Estonii i to będzie taka duża, mam nadzieję, ważna debata o roli państwa w cyfryzacji kraju.
Super, dziękujemy bardzo. So now we will switch into English. Aleksander and Krzysztof, the floor is yours. Thank you.
Okay, thank you very much, Paweł and Thank you for making this possible. I think it's very valuable what you are doing. So my name is Krzysztof Natusiewicz, and with Aleksander Buczacki, we have great pleasure to be a co-host of today's evening. Maybe just a quick start, a few words on us and the idea behind this topic. As was mentioned in Polish, so now in English, with Aleksander, we represent the Polish chapter of International Council on Systems Engineering, a worldwide organization aimed to develop and popularize systems engineering. And to be honest, with this event, we hope to start a countrywide discussion on this subject. I hope in coming years it will be more popular and will develop in this area. But now I think we should move to our guest, Aleksander.
Yes, I'm very pleasant to introduce our speaker. David actually is one of the best systems engineers I know. And then I started my adventure with INCOSE a couple years ago. I was very impressed by the speech of David. Then he was a president of INCOSE actually. And he actually told a lot about challenges for systems engineering and for systems engineers. And I hope that your speech today, David, will be as well as impressive and as usual, actually. So the floor is yours. And
very good. Thank you for the kind introduction, and I will try to live up to that introduction. This evening, we'd like to talk about systems engineering. If you are not an engineer, do not worry. This topic is one that is appropriate for all. And specifically, we want to talk about systems engineering in these times that we live in today. May you live in interesting times is a traditional blessing and a traditional curse. As we sit here in 2021, I believe it's fair to call these times interesting times in all the meanings of that phrase. But it's not the times we live in that define us. It's what we do, how we rise to the challenge, and how we innovate in times of opportunity and in times of adversity. Certainly, 2020 and to some degree 2021 will be defined as the time of the coronavirus pandemic. A complex problem with no solution that is 100% correct, no solution that is equally appropriate around the world. There are interconnected aspects. The virus itself, your physical health, mental health, economic impacts, and each of those with near-term and long-term implications. An approach that might work for an island nation, such as Iceland or Australia or New Zealand, may not work for continental Europe or the US. But let's take a step back. Let's try to recall a time before coronavirus. It's not that long ago on a large scale. Think back, rewind the clock to December 2019, before we understood that we were at the start of a pandemic. Even then, the times were still turbulent. At that point, many of us in the engineering field, but also in general society, were talking about the problems with the Boeing 737 MAX aircraft, an aircraft that suffered 2 crashes and 346 fatalities because of complexity and because of engineering error, among other problems. At the same point, at a societal level, we were talking about Brexit, the departure of the UK from the European Union. So if we look over time, we realize that we are in an age of evolution, an age of revolution. If you speak with a futurist, most futurists agree that we live in an unprecedented era of 4 transformations, 4 simultaneous revolutions. There is the digital revolution, characterized by unprecedented computing power and storage capability for data. There is the energy revolution, specifically the green revolution, as we move from carbon-based fuels to environmentally friendly approaches. There's the closely related environmental revolution, when we have a greater understanding of our impact on the world around us and how we must change to live in harmony. And then there is the era of mass urbanization, a movement of people around the world into urban centers, dense cities. That may change here in response to the pandemic, but for the time being, futurists agree that there are 4 simultaneous revolutions which trigger a 5th cultural dimension. When I was a child, I remember paying for music and owning music. Now my children simply subscribe. Everything as a service. By the way, the 5th revolution triggers a 6th, which is people like me wishing for the good old days. However you characterize it, we live in a time of turbulence, violent or unsteady movement. Turbulent times are fundamentally disruptive, unpredictable, and uncomfortable. They are times of conflict, times of confusion, words that carry very negative meanings. But for those that are aware, for those that are willing to change, there is opportunity in turbulence. When you come out of the storm, you won't be the same person who walked in. If we look back over these last 15 months, there are some wonderful technological innovations and advances. There is a new plane that has been designed from first concept through production and test in only 36 months. That generally takes 10 years or more. And for the first time, that was done completely digitally. Currently, the Perseverance craft is on the surface of Mars. And not only is Perseverance on Mars, we have multiple spacecraft from multiple nations around the world conducting scientific missions. We have increased autonomy all around us, increasing our capabilities, increasing our safety. And for a light touch, in the event that you did not see it, at the end of last year, Boston Dynamics had multiple robots dancing together to the song, "Do You Love Me?" A wonderful illustration of innovation in times to come. The question then is, how do we adapt? How do we excel in this face of complexity? Changes at a grand scale create turbulence, and that pace of change is unrelenting. It's complexity alongside the turbulence, and it's not the complexity that defines us, it's how we react to it. Systems engineering has a key role to play as we adapt and ultimately as we excel in these turbulent times in the face of complexity. Adapting and excelling is not easy, but I believe there are 4 key steps that help point the way. The first step is simply understanding what is different today. And I will tell you that through the eyes of a systems engineer, I see the world through a specific lens. For millennia, we have had notable infrastructure around us. In particular, very complicated infrastructure in the form of bridges and dams. But that's not actually what we consider complexity. We consider that to be complication based upon the sheer number of parts. When you look at the parts in a traditional dam, there are very few connections between the parts. one block next to another, positioned in such a way to distribute the load. That's the face of yesterday's complexity. The evolving challenge is different. If we move from infrastructure to the products that we build, to the products that we use, we see this evolution. From products, physical products that were built with mechanical and electrical components, then we added software to create smart products, products with integrated sensors and controls to increase the capability and the usability, the experience. Then we connected those products together to create greater awareness, exchanging data, and enabling new capabilities. Then we connected those products together in an intentional way to have a product system, a metro rail car connecting with a signaling system, connecting with a passenger awareness system so that we know how much space is available on the train and how quickly it will pull up to the station. And lastly, we have systems that were not built to work together. They're called systems of systems, the assembly of things to meet societal needs. In the language of a systems engineer, this is a change of technology, but in changing technologies, we have also changed complexity. In a simple product, there may be many, many parts, but the way they connect is relatively limited. With today's software and electronics and the coordination and the collaboration, it is much more complex. Things are interconnected in ways that we never anticipated before. Those interconnections bring capability, but they also bring complexity. As an aside, not only do we have more complex problems, we are asked to solve them faster. If you're not an engineer, that's okay. These same concepts exist around us every day. And in fact, part of the challenge is for us to take thinking that allows us to develop the next smartphone, the next smart vehicle, and improve those 4 revolutions, those challenges of environmental, energy, etc. If you are aware of the UN Sustainable Development Goals, those are grand challenges that are highly interconnected, much in the way that our response to coronavirus is interconnected. If you think about a smart city, it is infrastructure working in concert with sensors and software to deliver the right human experience for the people who live there. Germany introduced a concept called Industry 4.0. Japan has introduced a concept called Society 5.0. How do we bring technology together in a new way to create solutions for better human life and greater harmony with the world around us? In each case, these are problems that are highly interconnected, highly coupled. A small change in one place has a ripple effect throughout, and in some cases, the butterfly effect occurs as well. A small change can have large unanticipated effects. The challenge is using our traditional approaches will not solve these problems properly. If we use the mechanistic approaches of yesterday, we don't understand those interconnects. We tend to believe that applying technology to problems makes them better. In reality, applying the wrong technology to a problem and not understanding those interactions, pointless at best, destructive at worst. What has happened is, in place of things that have lots and lots of parts, but very simple connections, we now have even more parts tackling harder problems with more advanced technologies, with teams working around the world with problems that change as we try to solve them. Everything is interconnected. So the world has changed. How do we react to that? A systems foundation provides us a framework to address this complexity. Systems and holism looks not only at the parts, but the interrelationships and the interactions between them. This does not replace traditional thinking. We need traditional thinking. This is an additional layer that allows us to see the parts, the interconnections, and the whole, developing the picture, the capability that we need. Let me put this in simpler language for us. Let me be very practical. If you built small storage buildings, a simple shed, and you built many, many sheds, perhaps you could do so without plans. You would simply know well enough how to build a simple one-room storage space. If you were to build a house, that's more complicated. Even if you build houses every day, you likely need some form of plans to make sure the structure and the plumbing and the electrical and everything else fits together the right way. If you built an office building, a skyscraper, you absolutely must have that architecture. As problems become more complex, as technologies become more complex, as things are more interconnected, we need that architecture so that everybody can see the common plan and how the pieces work together. That's what systems engineering seeks to do. Systems engineering is a transdisciplinary approach. In other words, it is involved in complex problems that require more than one specialist to understand the problem and solution. And the systems engineer works to connect those specialists to take their insights so that together we can better understand the problem, better understand interactions, and find a better solution. Underpinning systems engineering is something that does not require engineering at all, and that is the concept of systems thinking. Systems thinking is a way of looking at the world so that you not only see the physical things, but you see the interactions between them. That is what we need if we are going to solve problems where a small change may become a small change, or a small change may become a big change. For example, if we speak of a vehicle, we could look at that vehicle in terms of its pieces: the chassis, the wheels, the drivetrain, the motor. If we took that vehicle apart, the parts alone will not move you from one town to another. It is only when the parts are assembled the right way with the right interactions do you have mobility. In doing that, that thought of how we bring the pieces together is systems thinking. We also then use that approach to say, how do we engineer the right motor and the right tires so that we can have the right vehicle with the right fuel efficiency and the right level of comfort? You would not take that vehicle and replace it with an even better engine and even better tires and expect it to have the right results. In this modern world, in this turbulent time, we need to define not only the right pieces, but we must also define the way those come together so that they give us the capability we want. If we think about a building architecture, that is very simple. If you don't build it the right way, there is no place for the plumbing to run, or the building may fall down. Products and societal needs have the same architecture. So this systems approach of looking at the interactions alongside the parts is about architecting the right solution. Fundamentally, It's about delivering the right, predictable outcomes in complex endeavors. How will our system interoperate internally? How will our system interoperate with the user? How will our system interact with the world around it? These are the questions, looking at those relationships. And at a very simple level, it comes back to managing 4 ideas. There is an idea called requirements or needs. What is it that we're trying to achieve? A system's why. For example, I might wish to support an island of people who live 500 meters offshore. Those are requirements. Behavior would be the actions that need to be supported. I must be able to move people to and from the island. I must be able to move food to the island. In an emergency, I must be able to evacuate people from the island. That's behavior, what we must accomplish. Architecture is how we will accomplish it. I don't know yet if the right answer is a bridge. Perhaps that's a very expensive answer. Maybe a ferry is a better answer. I don't know. And then verification is how we prove that it works. And so systems engineering takes the idea of systems thinking, looking at these interactions, and puts it to practical use to better solve problems. But systems engineering and systems engineers don't operate in isolation. The entire theory of systems engineering can be summed up with the expression, the whole is greater than the sum of the parts. The things that we build, we want to build in such a way that when we bring the pieces together, they work right and deliver the experience and the capability that people want. Systems engineers do the same thing for the engineering team. They bring the specialists together in a way that allows us to understand problem and solution and hopefully find the right solution to the problem that our users, our customers, ourselves want. In doing so, in connecting these various experts, we also enable innovation. We often think of innovation as the genius who suddenly has the grand inspiration. That certainly happens, but more often than not, as Henri Poincaré points out, innovation is bringing together existing ideas in new ways. The Gutenberg printing press was actually innovation by combining several new technologies rather than being one unique act of genius. So if systems thinking, if systems engineering helps us look at these interconnects, then how do we use it? Well, first we must understand that systems engineering as a named discipline has existed since perhaps the 1940s or the 1950s. But the systems engineering of yesterday is not sufficient today. 20th century systems engineering is not well suited for 21st century problems. So we must transform the practice as well, though systems thinking and the main principles of looking at interactions are timeless. So first, we must embrace today's technologies. One of the great systems engineering successes was the Apollo program, putting a man on the moon. But that was largely mechanical, with some electrical and very little software by today's standards. There is more capability in an electronic greeting card than there is in the computers that powered Apollo. Last year, SpaceX launched their crew cabin, a completely different technology. It's all about software today. And this software yields great capability, but also great complexity. We must know how to deal with that interconnect. Also, in the age of Apollo, we were largely after one thing: technological innovation with very, very high quality. But we can use systems engineering for many different reasons. We can use it to go faster. We can use it to be more responsive. We can use it to be more creative, or we can use it to drive higher quality. We need to tailor the approach to the business need and to the specific problem at hand. The way I would engineer a SpaceX rocket for quality is different than the way I would engineer a cell phone. A half-second outage on a cell phone is annoying. A half-second outage on a rocket during launch makes for a very bad day. So we need to tailor these approaches to the problems, still understanding the interactions, still generating the results our customers want. In doing so, much as the story of the plane that was engineered and put into production in 36 months, we must be rapid, we must be fast, we must be agile. Problems change shape as we try to solve them. New technologies are released. Competitors deliver new capabilities. So problems do not stay fixed as we solve them. We must evolve our practices so that as change happens, as customers want new capability, we can evolve with them. We need to fold the concepts of agile into the concepts of architecture. We also need to change our mindset. In some cases, we used to think, build once and have it last forever. In other words, when we built the Apollo program, we did not expect it to change. We built it, we launched it, we used it, we were done. But now, if you have a modern vehicle, your modern vehicle may change every night as it downloads new software. We must understand how we take the lessons of software and evolution so that we can not only be agile as we develop new capabilities, but once we have delivered something to meet customer needs, we can continue to evolve it as needs evolve as well. What this leads to for systems engineering and for engineering as well is an even bigger concept called digital engineering. Digital engineering is the idea that rather than disconnected approaches of CAD for mechanical engineering or ECAD for electrical engineering, and all these disconnected stovepipes in the engineering process, we should be able to have a connected engineering flow. The moment you hear the word connected, think systems thinking. The moment you hear the word connected, think systems engineering. And so how can we better connect the way we develop new solutions to problems so that we have a better flow of work, a better flow of information, we better leverage the digital revolution? That is called digital engineering. It is much bigger than systems engineering, but systems engineering is the enabler, the technical connective tissue that connects all those disciplines together in the same way that the systems engineer connects all the subject matter experts together. Systems engineering is about connections. The whole is greater than the sum of the parts. Through it all, I said the principles don't change. If you're looking to make systems engineering easy, I'm sorry, that's not going to happen because we're doing complex things. If you're looking for the easy button through software, through tools, that will not happen. We have to remain grounded and understand what's called the law of conservation of systems engineering. Put simply, this says once you identify a problem, the amount of systems thinking required to solve that problem is known. For something that you have solved before, less effort is required. For something that is brand new, more. For something that is relatively simple, less systems thinking is required. For something that is very complex and dynamic, more. So the amount of systems engineering is determined when you pick your project. Your only choice is when do you leverage it? Do you leverage it up front when it's most powerful, or do you do what most project teams do? They bring their best and brightest together at the end when things aren't working, when pieces aren't fitting together. That is the most common, but also the most expensive time to do systems engineering. So the challenge is evolving through more connectivity, more complexity. A systems foundation allows us to understand and respect and leverage those interconnects. And we can transform the way we do systems engineering from 20th century to 21st, leveraging new technologies, responding to new needs. But there's one more step in what we must do, and that is we must lead. The systems perspective is rarely the most powerful voice in a room, unless you're in a room full of systems engineers. But it is an important perspective to bring to any conversation. The conversation of how to effectively respond to COVID and these interconnections, there needs to be a systems voice in that room. The conversation of how Perseverance came together to work on Mars absolutely had systems engineering. If you're developing a new part of an automobile, a new smart technology, systems engineering has a role there. So we must lead, but we do not lead from the front of the room. We lead by influence from the middle of the pack. We have to embrace the relevance, the way we interact with others, the need to embrace the human side, the need to change traditional approaches. The first way we must lead is understanding that sometimes we have to do it right. We don't always have the opportunity to do it over again. It's always good to laugh at Americans. We give the world plenty of opportunities to laugh. One of these was healthcare.gov, the website that was established to allow people to sign up for government healthcare. $576 million spent on a website that allowed less than 100 people to register on day one. I'm pretty sure most technology companies could do better than that. The average person thinks that that was an IT problem. It was, but more importantly, it was a systems problem as they tried to bring multiple existing capabilities together. Okay, that's a humorous story. We can simply laugh at the Americans. I'm glad we can help you out in that way. We do it very often. We do it very well. Sometimes we can't do it over again in the area of product. We must do it right the first time. Before the 737 MAX, there was the story of the Boeing 787, an entire class of planes that was grounded not once, but twice because of overheating problems in batteries. Or something simpler, something closer to you and I, the Samsung Note 7, January of 2017, $5.3 billion worth of damage because of two different battery issues, one manufacturing, one design, both of them systems errors. It is amazing that Samsung survives as a cell phone provider. Economic damage, nothing more than that, but sometimes there is something more. If you look at the problem of invasive species, sometimes humans do it accidentally. Many times we have done it intentionally. In 1854, the Australians imported the European rabbit for hunting purposes. very prolific animals in terms of breeding, of having new young, it destroyed a great deal of land. So then you bring the red fox over a year later for hunting, a very elusive predator that is very good at killing the native population. And then in 1935, more recently, you bring the cane toad over to control the cane beetle. Again, a prolific breeder that generates a toxin that kills native animals. We rarely understand our impact in the world around us. Hopefully, we do so going forward. And sometimes there's human life that's lost. We recently marked the 10th anniversary of Fukushima. To quote the lessons of Apollo 1, it was a failure of imagination. No one thought through the possible flooding of the generators. No one thought through all the interactions with the environment. In the US, there's the example of the Chevy Cobalt. This was a vehicle where there was a weak spring on the ignition, and the ignition could rotate while the car was running, and it would shut off. So now you have a car in motion without power brakes, without power steering. Even worse, shutting off the ignition power turned off the safety systems. It deactivated the airbags. Even worse, it took a major car company 2 years to understand what seems to be a very simple connection. 124 fatalities, 274 injuries, 2.6 million cars recalled, lots of economic damage, but the cost in human terms is even higher. The first story of influence is when it comes to interactions, sometimes we don't have the opportunity to do it over again. We must do it right the first time. In leading this change, yes, we must understand the system's perspective, but we must also understand all of us have the system's perspective. There are some people who choose to make a career out of the system's perspective, but all of us are born with it. In the US, a small child of the age of 2 or 3 years will constantly ask the question, why? Well, some people believe that is to annoy the parents. Why? In reality, it is to understand the interconnects in the world around us. How do these things happen? Our brain is born seeking to understand that. Now, education makes us better specialists in narrower and narrower areas. If we are to deal with complexity, we need to reawaken that system awareness in everyone, not to turn them into systems thinkers, not to turn them into systems engineers. We need the skills that they bring today, but to make them better equipped to help all of us together solve these complex product problems, these complex environment problems, these sustainable development goals. If we want to lead, it's beyond seeing the big picture, seeing how the pieces come together. It's about setting the big picture so that every player who is playing a role in developing an answer, developing part of a technology, responding to COVID, understands the context around their part, they can make better decisions. The theory is, if you're in an interconnected world, you need to understand those interconnections, those interactions, so that when you're doing your work, you can make the right decisions. Fundamentally, it is about leading a change to complement the existing way of thinking with a new way of thinking that helps us understand these interactions in our solutions, these interactions with the world around us. In doing so, sometimes we may have to spend more money up front, but we generate more value in the process. How do you help people understand? You explain these stories of unintended consequences, but try not to scare people. That's not healthy. Try to simply illustrate with some non-threatening examples the power of interactions and how we must harness them for the intended reasons rather than these unintended problems. Ultimately, there's an author called Daniel Pink who wrote a book called To Sell is Human. Daniel frames that we need to convince people about anything, in this case, the power of systems, through the concept of attunement, buoyancy, and clarity. Those are difficult words in any language, but it effectively means speak in the language and the concept of your audience, be uplifting, paint the picture of a better future, and be clear in the benefit. For us, the benefit here is the opportunity to adapt and excel in these times of complexity. And buckle up, fasten your seatbelt. This change is happening. This change will not go away. Throughout our lifetimes, we will be in turbulent times. We, through studies, know that all programs benefit from the right amount of systems engineering. This is a specific aerospace and defense study, but it simply says, regardless of complexity, those projects that have more systems engineering understanding fare better than those with less. As problems get more complex, high systems engineering understanding translates to a 62% chance of success. Low systems engineering understanding translates to a 69% chance of failure. Projects that apply SE best practices perform better than projects that do not. Why? Fundamentally, we are using the collective intelligence of the team. It's not that systems engineers are superior. It's that we are connecting the ideas, the insights, and the knowledge of the specialists to get the right understanding of problem and solution early in the program. So we integrate the team, we integrate the knowledge, we understand the problem, we define our interconnects, we make sure there are no gaps in the solution, we continue to understand the why. The collective intelligence of the team is what we need to solve complex problems in turbulent times. And so this is the age of complexity. This is the era of change. Whether you're building a new product such as a video drone, whether you're solving a sustainable development goal, in either case, the systems perspective is essential to solving these problems. The interesting things live in the gaps between disciplines, between technologies, between the parts, where no one else is looking. That's why we need to complement traditional approaches with systems approaches. And without this systems perspective, we cannot address the challenges of today and tomorrow, free from negative unintended consequences. We need to do so effectively. Human and societal needs drive engineering challenges. Addressing them today requires holism, big picture thinking, and reductionism, what has brought us to this point. Today, we are the legacy of all who came before us. The question to us is, what legacy will we leave as we face these turbulent times? The world throws us more daunting challenges. We dream bigger dreams. Only if we can look beyond the traditional techniques to complement with these systems ideas can we see the real problems and can we bring the right solution. Through these ideas of complementing traditional approaches with systems engineering, we can tackle these wicked problems. We can explore new horizons. We can innovate in these times of turbulence, And I firmly believe we can leave a better world for the generations yet to come. Thank you. And with that, we will turn it over to questions.
Thank you, David, for this great presentation. Okay, so I'll start with one of the questions of our listeners. Actually, what is your take on how to work to become a systems engineer? And I will, on top of that, ask what, in your perspective, is the best way to educate systems engineers at universities, like 5 years of full course focusing on systems engineering, or rather 1 year specialization for already experienced engineers?
Two very good questions, Christoph. So I'm going to answer the second question first. The traditional belief is that to become a systems engineer, you are better equipped to have existing technical knowledge, 5 years of engineering coursework and experience, and then bring systems thinking on top of it. The reasoning behind that is the practical experience from engineering helps you understand these types of problems. These types of problems can be very abstract, difficult to get your mind around. So the most common path, and often the best path, is to take an existing practitioner, often an engineer or a physicist or a mathematician, but somebody with real world experience, and give them additional training in the area of systems. If you wanted to pursue these system studies, it is essential to combine both academic study on the ideas and practical experience. Hopefully you have a university near you that teaches these courses. If not, we have the benefit of technology and massive online open courses that do teach systems engineering. There are some very good ones. But the reason that you must complement academic thinking with practical experience is systems engineering is learned by doing. I could teach you the basic ideas of systems engineering in 4 hours, but it takes practice to actually address complexity effectively, and the two must come together.
Thank you. Aleksander?
Yes, David, I have, maybe it's related to the Poland question. So it's what you mentioned that actually the systems engineering is should be applied mainly for the critical complex projects, big projects especially. And do you think what could be a role in for such country like Poland, role of academia and public authorities to encourage to using the systems engineering in practice?
So Alexander, thank you for the question. And let me clarify, I believe I misspoke. Systems engineering is appropriate in almost every effort. Unless you have done it many, many, many times and you know already how to do this, systems engineering is appropriate. It is simply more important the more complex you get. So I think the role in any nation these days is understanding that the pieces that we build are now interconnecting in new ways. We may build the big thing. We may build the SpaceX capsule, or we may build a part that goes on the SpaceX capsule. In either case, we are dealing with some form of complexity, and there's more complexity around us. If we can help people just better understand that simple idea, and the idea that we have to look at interactions, then the pieces that we build will be better themselves. And the pieces that we build will work better in the supply chain as part of a bigger solution. That's relevant regardless of what you're doing at any point in the world. The last thing that I'll say, all of us are humans on planet Earth. All of us are interacting with the environment in some good ways and in some bad. This systems thinking, this systems understanding is therefore very relevant as we deal with the environmental revolution.
Okay, thank you.
Okay, another question from our viewer. That one is about MBSE. On one of your slides, it was mentioned. Could you give an example of how it can be used? Is it mainly about working on a database describing the system? And at what size of a project it should rather go with model-based systems engineering instead of non-model-based systems engineering?
Very good. A sophisticated question. So model-based systems engineering, for those who are not familiar with it, is analogous to moving mechanical engineering from hand drafting of drawings to CAD, to computer-aided design. So it allows us to move from document-centric approaches capturing the knowledge of a systems engineer to higher fidelity models. It is the injection of digital technology to of low complexity. You can still apply document-centric techniques, particularly if you've solved that kind of problem before, no new requirements, no new technologies, no new risks. If you're dealing with something that is complex, if you are interacting with many other people, if you are part of a supply chain, then making the transformation to model-based and computer databases and interconnected data will help you do so, and the tools help manage your knowledge to reduce engineering errors. The human still does systems engineering. The tool just automates bookkeeping and diagrams and reports.
Thank you. Aleksander?
Another question related to MBSE. So do you think that it's at the start, it's better to use the, let's say, standard like XML language, or better, use the domain-specific languages in the projects?
It's an interesting question. I would say that the answer, if you ask a systems engineer an or question, they will often answer with and. And I think this is a case where and is true. So in this case, we need to blend two ideas to truly have the connection across the team. There are some ideas from the system language, such as SysML, that help us understand how requirements are satisfied, how pieces interconnect. But we also need some of the domain language so that we can express the critical ideas of the problem and of the technology. So you need some of both. At the highest level architecture, you need the systems language and then complement it with the domain.
Okay, thank you.
Again, one from our viewer. How to sell systems engineering in an organization that tells you why spend so much time on the requirements and talking? Let's start doing things. How to make those first baby steps? As we said with Aleksander, we are starting in the domain as Poland, so maybe it's an important question.
Yes, it is a very important question and a very common question. So you need to sell systems engineering in response to a challenge or a business problem that you have. We like to think that we change for a better future. The reality is we change in response to pain. So is there a pain that your organization has faced on a previous project? You have lost control of requirements. You have had errors occur late. You have had knowledge lost through time. Identify an error like that and develop a lightweight, remember, tailored approach of systems engineering that is thin enough to just address that. And then we can build that out over time. But if you can point to studies such as the one that I did, which shows systems engineering is critical, but the managers will simply nod and say, yes, I understand, but no, I cannot spend the money. You need to tie it back to an existing problem where they have already felt pain, felt expense.
Thank you.
David, I have like maybe a little bit different questions. In your opinion, how many systems engineers usually should be involved in the project, you know, relating to another engineering stuff? And what's the criteria? Because I think that in one kind of projects, probably it's needed more, and another project less systems engineers. In your opinion, in your practice, actually from your practice, how is seen?
So even on the largest of projects, you do not have large numbers of systems engineers. It is a much smaller number than any other kind of engineer. So the question then becomes, how do you start to tell how many you need? It goes back to that idea of the conservation of systems engineering. If you have solved this kind of problem before, fundamentally, and there's nothing new, no new performance, no new technology, you probably don't need any systems engineer, okay? If you are making small changes to an existing solution, I have built this thing before, but I'm trying to create a next generation. And I've got some lightweight technologies, but fundamental or lightweight changes in my requirements, but fundamentally we understand this. It may be one systems engineer joins the team to help set up that architecture and ensure that we're not overlooking anything. If you're tackling something brand new, you have never solved this problem before, or you're trying to solve it in a fundamentally different way, now you need a team of systems engineers along with the critical domain experts so that you can properly understand problem and solution.
Okay, thank you.
Okay, maybe two quick ones from me. As a former president of INCOSE, what is the value in INCOSE membership? To whom would you recommend it to? And the second one is, what does systems engineer do on daily basis?
So speaking to INCOSE, if you associate with these ideas of systems, then INCOSE is the body for you, because it is your ability to connect with not only a knowledge base, but more importantly, a practitioner base of 18,000 people around the world applying systems engineering in different ways on different projects. So you gain access to not only the knowledge, but the people. And remember, systems engineering is learned by doing, so that shared experience is key. In terms of what a systems engineer does on a daily basis, the answer is it's very, very different. But fundamentally, what they're working with is trying to develop that architecture. Think of the analogy of a building architect who is doing the design. They're not actually doing the building, but they're doing the design to make sure that it satisfies the customer, it makes people happy, it supports things, it flows, there's room for plumbing, etc. We are working with the domain specialists to put together high-level architectures just in a different concept, in a different language. We're thinking about what the system must do. We're thinking about the available technologies. We're thinking about mappings. We're tracing requirements to make sure it'll work. That's what we're doing in a generic way. Go back to the analogy of a building architect is probably the best analogy.
Okay, thank you. I don't know how much we can stretch your time. Maybe last 2 or 3 questions, Aleksander.
Okay, so maybe one question. So it's in Poland, actually, the lean management is quite common, I think. And do you think what's our relations actually lean management and systems engineering? It is could be like seen that it is something. There are some similarities in your opinion. What's your opinion on this?
So the two are very complementary if systems engineering is done right. If systems engineering is seen as a set of processes that must be executed, then systems engineering can actually be anti-lean because it is not focused on outcome. However, if you understand that your job is to tailor systems engineering to do the right processes, to answer the right questions at the right point in time, systems engineering is effectively designed to avoid rework and to avoid waste. And so, done well by a good systems engineer, we put in a framework that is very compatible with lean, and then you go to the right depth at the right areas to answer the questions that you need to know deeper. Complementary techniques, different language, but very complementary techniques.
Okay, thank you.
Okay, so maybe last from me and then last from Aleksander. So systems engineers are working with specialists in different domains. So how much of this different domains should systems engineer know? I think about percentage to cooperate well. In your view, of course.
A very good question. So a systems engineer cannot be an expert in everything. That is not our job. What we have to do is we have to know just enough of the domain so that we know who to talk to and trust as the expert, and we know enough to trust their answer. So we're not talking about 50% knowledge. We're not talking about 25% knowledge. But you cannot be completely ignorant either in that domain. You must, if you're doing a software-centric solution, you have to understand the basic ideas of software and networks, etc., so that you can have the right conversation with the expert and you know who to trust.
Thank you.
Okay. So maybe last question. What's, in your opinion, is the biggest challenge for the systems engineering in coming times?
There are so many dimensions, Alexander, to answer that on. I'm going to pick two. Okay.
Yeah.
I will cheat and give
the biggest one. Yeah. Okay.
Right, well, the biggest one is the question that Krzysztof asked, which is, how do you convince somebody to do it? Because if you're not doing systems engineering, then you're not seeing the value. And so making the case and convincing people to use it is the biggest challenge. If I think about the changing world around us, the biggest disruption to systems engineering is actually artificial intelligence. Not using artificial intelligence for systems engineering, but understanding how we use systems engineering to properly engineer systems with some degree of machine learning and evolution. We have to continue to evolve our practice, our discipline, as technologies evolve.
Okay. Thank you. Thank you, David. Thank you for your great presentation and your answers. Thank you.
Thank you for the
maybe I will
opportunity. I've
only
enjoyed
add. Thank you, David. I will only add at the end that in parallel we are discussing with Pavel and Bartosz possibility of next presentation. This time it may be on the subject of healthcare from someone you, David, know, our good friend Bogdan Ovenheim. We'll keep you posted if it works out.
Of course. Thank you, Krzysztof. Thank you, Aleksander, and of course, thank you, David. Now, me and Pavel, we know a little more about system engineering. Thank you very much. It was great, inspiring meeting and evening. We would like to promote our WEinnovators Club to other people, and of course we are open for every opportunity. So I would like to say to everybody that if you have any ideas who's we could invite here, we are very open. So David, now I understand that system engineering is the best way to innovate, and I know that without your discipline, we could not do anything fast and very well. Thank you very much. It was really inspiring evening. Szanowni Państwo, bardzo dziękujemy. Thank you everybody for spending this evening with us, and I hope we will see next week. See you. Bye bye.
Thank you. Bye.
Bye.
Thank you.
Thank you. Bye.
Thank you. And stay safe and healthy.